Hello, everybody. How are you doing? So we are back. We have the Enceladus. I think she's here.
Hi, everyone.
Yeah, she's here. All right, cool. We missed last week, but we are back on. Now we're pretty much getting to the end of C as an additional language, the basic course that we outlined. And it's been a fun adventure, hasn't it, Jess?
It's been a lot. I'm actually surprised that we're already kind of at the end. So.
Yeah. Well, I mean, we're going to be probably doing some project stuff, but I mean, that's basically C. I mean, the idea here was to get through the C language. So this original topic was topic 10, and it was, sorry I didn't update the web page, but this was kind of the everything else. So as I told Jess and I promised her in a previous class, we'd done the good C, and now it's time for the bad C. So we've done the pure true C. And by the way, hello Loafbone. We're gonna get just dirty with the language now. So we're gonna focus mostly on bitwise operations. I think that they're all pretty dirty. So we're gonna do a quick little review of some of that stuff before we throw Jess in the deep end on that. And then we're also going to understand the rest of memory and the way that programs execute, because we're at the end of C, so we could build a loader, we could build a kernel, right? We want to build a whole operating system, chunk OS. This is the time. So let's kind of get into it. So I just want to show real fast before we get going. Here's Jess. She just did a epic stream with a shave. Shave head. But this is so just what I was showing you here. This is kind of the topic that was here. We're going to split this part out. So we'll take the randomness stuff and put that in sort, and we'll put that into a separate section. I think that this stuff with the basic bit stuff is really probably a lot harder. So I don't want to try to junk up too much in a single session. So I'll get that updated, but let's just dive in. Are you ready, Jess?
I am.
All right. Well, let's go for it. So I'm going to throw on the glove because we're going to need some whiteboard fun. And we're going to review what we know about our machine, because we know everything about the machine. Maybe not everything, but feels like everything. We know something. No, we know everything at this point. It's all about libraries right now. Team Chunk, nice. Okay, so we have two major topics. So we're going to talk about bits, and we're going to talk about the heap. So bit, do you remember? It was a portmanteau. Do you remember what it was short for? We had a little bit of trivia in that class. It was a long time ago, because I think it was like our second session, to be honest.
Binary.
Yep.
I'm guessing here.
Yeah,
binary,
no, good guess. It's actually the end of the word.
Okay.
Digit.
Okay. Yep,
So
that makes sense.
that's a bit. All right, so it's a 1 or a 0, and that typically corresponds to our notion of true and false. And this is something we can implement in logic. And I don't know how much logic. I'm going to guess that you don't do a lot of bitwise logic in Python. It's not really unnatural for the language. So I'll, at risk of being a little redundant here, I'm going to just very quick version of logic. So this is two-state logic. So this is classic two-state logic. It's also referred to as boolean logic, named after the dude who invented it, Mr. Boole. And he likes things to be true or false.
Does that actually work?
Oh yeah, that's totally true.
Wait, seriously?
That's actually.
I often wondered about the origins of that word.
That's a person's name.
Okay.
So the actual Boolean logic in its pure form, we are not doing. We're going to do the computer science current day version, what you need to know for programming version. I'm not going to go too much into all the kind of craziness there, but there is
So So my discrete logic classes from
This is
philosophy
totally your
won't help?
discrete. Yeah, no, they will totally help. But we're not going to do Aristotelian logic. So I don't know how much of
Oh
that you've.
man, that actually I feel good about. All
Yeah,
right.
that's
Crap.
like you've got your, for some, for one, for oh
Oh
hey, what's up,
yeah,
CCV?
syllogisms.
Okay,
Throw me
we
in. I
we
got syllogisms down, but not so sure about the
no,
bitwise stuff.
we're just not we're just throwing that out. We're 2,500 years later. We have
All right, I don't
advanced.
care.
We're gonna go crazy. We're just going back to 2 states. Aristotle had a whole bunch of states, but we're not doing that. We're not doing Aristotle. We're doing our Mr. Boole, and Mr. Boole said things are either true or they're false. Okay, so if I have a single variable and I name it p, because you need to mind your p's and later you're going to mind your q's, but let's just say that this literally what this comes from. So if I have variable p here, and it can be either true or it can be false.
Mm-hmm.
All right, and then I have a variable q, and it can also be true or false. But I'm interested in all the combinations of this. So there's p true, and then there's q true. There's p true and q false. There's p false and q true, and there's p false and q false. So that would be the 4 combinations of these, right?
Yes.
All right, so if I put that on a table, is this something you've seen before? Sorry.
Yes.
Okay, so if I have this is true, and this is true, this is true, and this is false, this is false, this is true, and this is false, that is false, that's neat. Okay, now we can combine them, and we have 3 basic operations. Do you remember what they are? I don't see. This is the reason I'm asking is because I don't know how much is just going to be just super boring review and how much of this is going to be kind of fresh. So
3 basic operations, mathematically speaking.
Well, for these 2 variables, yeah, mathematically in the boolean world, there's only 3 things we could do to them, and you've heard them. You've definitely heard them in Python. So all right, at risk of being redundant, we have yeah.
Okay.
We have p. We have not p.
Not p.
We could do not q, which is really the same thing, but we could do p and q. I'm not going to write the formal notation for it because it's boring.
So chat is saying, by the way, that apparently I'm super quiet.
Oh.
I'm generally speaking a loud person, so.
Oh, let me turn it. Oh no, that's because I had music blasting. Let me know, chat. Let me know, is this better for when she talks?
Joking.
Well, don't do that. Okay, so 25% of you. Okay, so I think I got that up, but good catch.
Right.
Let us know if that is not good.
Thank you, chat.
Okay, so
so and not.
Let's clear our screen here. Let's mind our p's and q's. So we have a p and we have a q. All right. This is true, true, false, false. This is true, false, true, false. This is just the short way. I mean, these are all the combinations.
Yeah.
Okay.
You're good. And then operations being and, not, and or.
Yeah,
right?
we could write the formal math notation if we really want to be boring, but.
Hey, that actually might be more familiar for me. No, but you're fine.
Right. Well, I should, if I'm going to write the formal notation, I should write it correctly. Usually you start with and, which is that one, and then then there's or, and then there's not, which I guess in formal would be kind of like that. But let's be computery about this and not do that. Let's just write it out because we're like that. So p and q.
Mm-hmm.
P or Q and not P. We'll just do not P. Actually, I'll use the tilde version. So not P. All right. So not P is the easiest. Give me the values top to bottom.
False, false, true, true.
Yeah, piece of cake. It's just whatever the opposite of this first column is. So that's all right. P and Q. This is when both of them are true. So there's only one case.
Which is the top one, and so then it's the rest are false.
All right, and then or this is either one of them, or.
So the first 3 are true, and then the last one's false.
True, and false. Okay, I don't know if you covered XOR.
So I have looked at that because it was in this book of preparing for coding interviews, and then I was like, I've never used this, and I've never even needed this at all. So I kind of just
it's not common for like high level languages. It is common for bit languages. So
Okay.
like it is a very useful operation. For example, if you're reading a Nintendo controller, you're going to want this XOR. But
Gotcha.
it's like up in the higher level land, it's a very odd operation. Like it doesn't make much sense.
Yeah, I read the Wikipedia page and
Okay.
I remember
Well,
it making sense when I read it and then going, I never used this and it fell out of my head.
it's
So
just it's super sensical. It's literally it's one or the other, but not both. That's it.
yeah.
So it's exclusive or. It's just as opposed to you could call this inclusive or, which includes
Hmm.
both. And this exclusive or is just one or the other, but not both. So that top line where they're
It's
both
false.
true is going to be false. And the
Hmm.
bottom line where they're both false, it's going to be false.
Is also
But
going to be false.
here
Yep.
P is true and here Q is true. So at least one of them is true, then XOR is true. Okay. Now, because we're in C world, these all have notations. Now, you can probably guess them, but this is and, this is or, this is not. Sometimes it's just minus. It depends what kind of not you want. And this is a caret.
Yep.
Okay, so you'll probably use this the least, except if you're reading a controller or something like that. And this one is really common. And then this is when you're assembling lists is very common. But from a practical standpoint, you're going to be using these two the most often. And you are familiar with their doubled parts, like like when you're doing a logical and, or a logical or. Like that's more like like if x is equal to 4 and sky is blue, then do something. So here we use this double notation. This is not a bitwise operation. This is a logical
Yeah,
operation.
that's
And they didn't invent this out of thin air. They just took the bitwise and operator and they said, all right, well, that's we'll just two of those and you're good to go. So, and same story with or. So if you just take one of these, then this pipe operator. And for anybody in chat who doesn't know, that is the pipe is not a 1. If you were going to draw them to scale, this might be like a 1. But the pipe operator is a vertical bar, some people call it. But we call it pipe because we're Unix people, and it's for piping one thing to another. So
yep.
anyway, great. So we did our review of our truth table. Everything's a piece of cake, and we're done with bitwise operators, right? Okay. So how does this apply to C, you might ask? Because now we know what the operator is. Nice graphic, love fun. I appreciate it. So how do you apply this to actual values? Well, we're not dealing with single bits. There is no single bit type in classic C. There's some newfangled stuff, but we're not going to get into that newfangled stuff. We're gonna do classic C. So our smallest data type. What's our smallest regular data type? Like least amount of memory, kind of small.
Character?
Yep. Yeah, character. Now, we're going to be dealing, since we're not going to be interested in signs, we're going to be dealing with the unsigned version of it. So this will be an unsigned care, just because we don't want to allow any sort of negative thing. That'll be a little bit weird. But
Yeah.
we can get to that a little bit later. So how big is a unsigned care or a care? It doesn't matter.
8.
Yeah, it's 8 bits. So great. All of these operations apply to 8 bits at a time. And that's how C deals with them. So if I have a number, like, for example, the number 3 in regular decimal, which in hexadecimal is 3.
Okay.
And in octal, also 3.
Okay.
So turns
I
out when
can't pull that out of my head, but I will trust your word.
you absolutely can when it's less when the number is less than whatever the base is, it's always just the number. So the one place you're going to run into trouble, like, okay, so not in octal, not in hexadecimal, not in decimal, but in binary. What is 3? Well, it turns out 3 is greater than the maximum value you have in binary, which is 1, because if you go past a 1, it overflows. So the number 1 in binary would be 1, which is fine. The number 2 in binary would overflow because if I add 1 to this, I can't put 2 here. So I have to go to the next digit. So it becomes 1-0. And the number 3 in binary is going to be 1.
1-1.
Yeah,
right?
because that's it. So it's not too hard when you're down on these like small numbers to figure it out. Okay, so if I represent the number 3 and I assign it to a char, so if I have my, and I'm just going to write the short version of this. So this is a u char t kind of thing, which is just this thing. Then, and I call that x, and I say you're going to get the hexadecimal value 3. Doesn't really matter that I'm using hex because it's exactly the same as regular decimal anyway. Then that actually in memory is 8 bits wide because you told me that. Right, so that's all our chunks. And it just means that these last 2 bits get activated. So this turns into 1, 1, and all of these are zeros. Okay, now if I have the number 4, so if I take u char t and I say y is equal to the number 4, and again, it doesn't matter what I put it in. It could be in anything. I'll just stay in hexadecimal, but really meaningless down here. So if I represent this number 4, what's going to happen binary-wise?
The third bit is going to be active from the right, and then the rest of them will be inactive.
Yeah, exactly. So if I go back to my diagram of that chunk of memory, and I split that up into 8 chunks, which correspond to our bits, then I'm going to end up, these 2 are both 0, and this one becomes a 1, and all of these are not active, as you kind of said. Okay, so I have 2 variables that are represented in memory. And these correspond to true here, and this is a true, and all these are falses. I can write them all out, but they're all false, right? There's notion of 0. And I go and I AND these 2 together. So if I do x and y, what am I going to get?
You are going to get all false?
Yeah, because where is
all
true?
Zeros. You're going to get 0.
Yeah, it's all false, which is zeros, and that's because none of them are both true, right? So it's going to go this one and this one, this one and this one, this one and, oops, not that. It's going to go this one and this one, this one, this one. And all of these, none of them are going to satisfy the AND condition. So that's sort of our translation into CLearn. So this is going to end up being all zeros, which if I have it all zeros for binary is the same as what number in decimal?
All zeros is just 0.
Yeah, it's just 0.
Okay. All right. Yeah. Sorry, there was a second there where I was like just doubted myself and
it's weird because when you're dealing with bitwise operations, you're wanting to think in binary because that's kind of where the operation's happening. But when you kind of come back to the real world of like decimal or hex or whatever, it's a little weird. And that's important. Like, that's okay to feel weird, but you have to understand that this domain of binary is what matters because that's where the operation's happening.
So I'm following you, and I follow, like, if you were to tell me, do or.
Well, we're going to do or.
Any of this.
How do we do or?
It makes sense, but I guess my question would be, why would we need to do things on a bitwise level?
I'm not getting into why at the moment. We're getting into the rest of the language, and that means you got to know what bits are. This is really important for something called bit banging in C, which that's an advanced topic. But let's worry about what you do with it later.
Okay.
For now, let's just go over what it is. So it's literally an implementation of those truth tables that you saw at the binary level. So you have to just treat this as 8 binary digits next to each other. Well, yeah, 8 bits in a row. So if I OR them, what am I going to get?
You are going to get 3 ones. So that would be...
the bottom 3 ones, right?
Yeah. So that'd be 6.
This is going to be 4 plus 2 plus 1.
7.
Yeah, so it's going to end up popping out 7. So this seems a little weird. And this seems a little weird if you're looking at the numbers. Because if you just looked at it as like x is 3 and y is 4, if you OR them, there's 7.
So it's like adding for that one example.
One example it is. But if I make this 2, then it's not adding.
Mm-hmm.
So yeah, it's dangerous to think about it in this domain.
In non-bit terms.
Yeah, whenever you're looking, and this is like a really common mistake and coding problem around C, is that you're looking at it and you're thinking about it in decimal or hex, but actually it's not happening in that domain. It's happening in this domain. It's happening in the binary domain. So it's super important to think about how many bits you got and what's happening at the bit level.
Mm-hmm.
And this is really important for stuff like Arduinos, by the way. So
Okay.
there's an awful lot of bit banging down on an Arduino or any sort of microcontroller. All right, so high level, bits make sense?
Yes.
Okay. Now, you can apply the same sort of operation. You could do an X exclusive OR with Y, actually, this is just a caret, the kind of thing you get when you do shift 6. So that's, same kind of trick. It's just either or. No problem with these two numbers because it's going to be the same thing as or.
It'd be 7, yeah.
Yeah, it's going to be 7 again. And you can also not this, right? And if you not this, then you're going to end up with all of these bits flipped.
Yes.
Okay. So there you go. There's your bitwise operators. Now, those are your basic bitwise math operators. So they're in that boolean kind of sense. Now, 2 more operators we're going to worry about, which is which are these. And you might have seen these in other languages. I'm not sure. But they're the shift operators. So this is, again, not something very natural in Python. It's not going to be common unless you're like dealing with microcontrollers a lot. But it does happen. And what is shifting? Well, it's literally just shifting the bits over. So if I have again, unsigned care, which is 8 bits, as we know, and I have a pattern in there. That was really bad last slash there. So let me just mop that up. All right. So if I have like 0, 1, 0, 0, 1, 1, 0, 0. Actually, just to make that interesting, let me put a 1 in the last digit. Okay, so if I have all these bits, now this represents some character, so I can turn this back into the decimal domain if I want. I don't feel like working it out. But it's there. So if I shift these over 1 position to the left, or that's the right, that's my bad. So if I shift these 1 position to the right, then what kind of pattern am I going to get? It's really obvious, right?
Yeah, just all the ones move 1 over, right?
Yeah. Now what comes in here?
0.
Okay, so this is sort of a argument. This is whether or not you're moving ones in or not, which becomes a problem with negative numbers for reasons we'll get to later. But
from a hardware perspective, like off is sort of usually the default, right? So it would make a lot of sense.
Trust me, there's years of argument. Now, what happens to this last bit? It goes to the great bit bucket.
The great bit on.
That's in the sky. We call that the great bit bucket in the sky. It just gets thrown. Now, it actually moves over to a special CPU register, but we're not doing assembly language. We're doing C.
So again, though, and totally, I know you said we'll talk about what we're going to use this for later. Having worked with Arduino and worked with microcontrollers, this makes perfect sense. The idea of shifting bits one way or another, especially when thinking about like gates and things like that, totally makes sense to me why you would need this. When you get to the level of like a programming language, though, then I'm kind of like, well, it's good to know when I'm building something, but when I'm thinking about the programming aspect of it, I'm really struggling with why I would ever want to shift bits left or right.
Why would you?
I don't know.
Yeah, that's a great reason. We're you know what? I'm going to tell you that in a minute. But
okay.
For right now, that is the right shift operator. And the way the right shift operator works is I specify a variable, and then I say I want a right shift, and then I specify how far.
And a status register? Sorry, I'm reading chat.
No. Don't worry about status registers. We're not that's that secret place that I told you about. We're not doing assembly language.
Is that the bit bucket in the sky?
And last miles is absolutely correct. Don't worry, this stuff is important. It's just
I trust. I have absolute faith that it's important.
Oh yeah. No, we're
trying to
gonna
make
get
those
to that.
connections.
Let's
Okay.
worry about how to do it for the moment. All right. So if I wanted to make this happen, which I just did an example too, I would write that as, let's say X gets this thing, and then this line would be X gets right shifted by 1 bit.
Yes.
Okay. Now it turns out we're sliding digits, and binary is power of what?
2.
Yeah. Right. I mean, versus like, dealing in decimal, which is a base 10 or power of 10 kind of world. And now when I shift in decimal, what happens to a number? If I take the number 17 and I shift it
You're shifting
one
by
position,
powers of 10. So it's an exponential.
It's the same thing as, in this case, I'm dividing by 10 if I move one place over. It's exponential if I do several of them. So this n would be that exponent. So
is an exponential. Even moving into the decimal is exponential.
Yep.
Yeah.
But I can think of it as just sliding the digits corresponds to division by 10 if I'm going to the right. And if I go to the left, it's multiplying by 10.
Right. Okay.
Turns out the same thing's true with binary, except it's not 10, it's 2.
2.
So operations that are like multiply by 2.
But we have operators for dividing and multiplying.
Multipliers and dividers are super expensive in silicon. So depending on what kind of machine you're on, now obviously any modern computer, it's going to be super cheap. But, that multipliers are not super fast. Like, I mean, it took a long time to get to a single cycle like multiply, and it was tons of gates. Last Miles, I'm sure, could write a book on this. So it turned out, like, back in the day, you'll see a lot of code that like involved, like, if you were dividing by 2 or multiplying by 2, you would shift, because shifting is super fast. In fact, the compiler will even flip it to a shift because it knows shifting is so fast.
Okay. So that makes sense. That makes a lot of sense, actually.
So this is important for, like, okay, so we can think of this, our first case for this is going to be fast multiply and divide.
Okay.
Now it only applies to if you're dealing with powers of 2. So that's part of why, we always tend to pick blocks that are powers of 2, right? If I do divide by 1024, I can do that super fast because I can just, it's this many bits. It's 10 bits. So I can just do a right shift by 10. That's divide by 1024. So yes, as Last Miles is saying, it is super fast because it works exactly. It's just the same way. Why can you multiply and divide by 10 when you're in decimal? Because that's just the piece of cake.
The structure of the language.
You just slide over the stuff. Okay, so that's pretty much it. So that's bits.
Okay.
That's basically all of the bitwise operators. Now, why? I'm not really getting into why too much, but I can tell you the one case that you're probably going to hit most in C is what are called flags. So in the case of flags, you're usually specifying something that's true or false for a bunch of values.
Okay.
So like one of the cases where this comes up all the time, and I was originally going to do it as our programming example tonight, but then I realized it's a lot of octal and I don't want to torture you.
Yay, less torture.
Is Unix permission. So I don't know if you've seen that dude on that streams RWX Rob. I think is his name.
I have very little time for watching Steam, so usually I'm very limited in terms of the streams I can watch.
Okay, well this, I haven't spoken to him, I haven't watched too much of his stream either, but I'm just going to take a guess what this is. This is probably corresponds to Unix permissions on a file.
Like read,
which would be
write,
read, write,
execute.
And execute.
Schmod.
Okay, now that actually corresponds to bit patterns. So back in octal land, when I had 3 bits, then this would be no permission. Then read was actually the high bit. So, and again, I'm using Motorola syntax here. So this would be read, this would be write, and this would be execute. Now you'll notice these only occupy one spot, right? So
but you can assign multiple permissions.
And how would you assign multiple permissions?
Having multiple bits be true.
Yeah, I might do something like I want read or execute. which would give me what in C land? Or is either one of them is true?
So you could have a couple answers there, though.
Well, only
right?
one answer for 3 bits, rather.
Well, so, oh, you mean like for the example that you just wrote?
Yeah.
Or
Yeah, read. So if you wanted to do read and execute, you could do this bitwise by doing read or execute, which would do what? What would you get?
You would need 1, 0, 1.
Yeah. And that's basically because you don't have write. So RWX Rob would be RWX.
Wouldn't you want read and execute, not read or execute, though, if you want both of them? Because either way, that's what I was saying.
What happens if I and them?
Read or execute, and you'll get 1,
0, 1.
Either 1, 0, 0 or 0, 0, 1. Both of those could satisfy read or execute.
No, not from a bitwise operation. So in a bitwise operation, if I OR these two, this one and this one, bit by bit, I OR them.
Right.
I take the 1 and the 0, I get a 1. I take the 0 and the 0, and I get a 0. I take the 0 and the 1, and I get a 1.
I see what you're saying. Okay.
So basically, to get this, like this is the execute, this is the write, and this is the read, then I need to use this OR operator. And actually, this is a really common use in Unix world of like bitwise operations. Now, as we're talking about, as I mentioned earlier, as Last Miles just pointed out, yes, this is octal because there's 3 of these. And this is kind of a deck-ism that we all get to. Long live deck. Rip deck. But this is kind of convenient because I can just use each of these bits as a flag corresponding to whether or not you have this permission.
Okay.
And you'll see this in C. You'll actually see like the way of actually specifying this is exactly what we're writing out here. You know, something like read or... And by the way, if I wanted to have all 3, I would do read or write or execute. And that would end up being 111.
Right. Yep.
And if I dropped read, it would end up being 011. Okay, so we're just doing bitwise operations there. So this is really, bitwise operations are really common for flags, and you'll still see them used to this day in libraries. It's still a common way to do this. I mean, I could just throw a whole bunch of memory at it and use one variable per permission, but it would be very wasteful in Silicon. So, and this was back in an era where we didn't have a lot of memory. Keep in mind. Plus, even if we did have a lot of memory, would you really want to burn all of it on like permissions on a file? Like, not really. Like, you want that to be compact. It's like, where'd your disk go? Well, it's all the permissions stuff. You know? Okay. So that's kind of a practical case where we would use it. If we wanted to read off these values, like say we wanted to test whether or not, so if I had some variable x, which corresponded to the permissions for the file, and I wanted to tell whether or not read was set, how would I do that?
I mean, so could you just do not?
Well, I don't want to flip all the permissions.
Well, not like set that equal to... Oh, I see what you're saying. Okay, so...
Like x is the permissions of the file. So I want to test, where's read? Which bit is it?
It's the... well, it's third from the right.
Yeah, third from the right. Okay, so how would I actually get that value?
I mean, could you just see if it's equal to 4?
Except that if there was write, then it wouldn't be 4, right?
Okay.
Right, because if you're right that like 4 is the number that it would be like operated with.
Only, yeah, I assumed only read. So you're saying like, how do you account for?
Right, yeah, this flags can be, you know, whatever. I mean, in this case, like you could have any combination of these. So like, you know, 4, I mean, I could test all the combinations. I could say, well, if there's 4 plus the equivalent of 4
all you would need to do is equal to or greater than 4. Because if the other ones are switched on and that one's switched on, it's just going to be a higher number.
Okay, well then how's your algorithm going to apply to testing for write?
Yeah, so like it would work with read, but it definitely wouldn't work with
Yeah,
read.
I mean, so I could test every single possible bit pattern that has a valid write would be one way to do it. Like, so I could count all the multiples that have write in them. Or there's a simpler way using the operators we just said. Which operator only allows it
Bitwise
through?
for
Yeah, which operator only allows it through if both are set?
if both are set is and, but
Yes.
we wouldn't want that.
Oh, we definitely do want that.
Why?
Because if I did this thing and then I went for the actual bit that I wanted. So let's say, like, for example, I want to have 100. So I want to check for read. Now, again, I'm assuming this is octal, but we're not actually going to code an octal, don't worry. So if I go and I and with this thing, the only time this is ever going to be true is if this thing also has that bit set. Right? If read is set on X and I and it with this 01, well, this 100 thing, then the only time that that's going to evaluate, like if read is not set, then it's going to be 0, right?
Right.
And if read is set, it's going to be the equivalent of 1 in this digit. Right? And so I can actually just and the thing with the bit that I'm after and then test whether or not it's 0.
But wouldn't so if you did just what you have there and you had 0 or why do we suddenly have 4?
Well, so there's two reasons. One is because I'm writing this as octal. Octal numbers are always prefaced with 0.
Okay. So in that case, like if we had 0, 1, 1,
Yeah,
and
last
you
miles, you're late.
anded the two, you would get 0, 1, 0, 0 back. You wouldn't get 0 or 1. I don't understand how you said that if it was read permissions, then we would just get 1. But I don't see how it's evaluating bitwise. So it'll evaluate the first two. And in my example, the first, starting from the left would be 0. And then the second one would be 1. And then the third one would be 0. The fourth one would be 0. So you would get 0, 1, 0, 0 back. You wouldn't get 0 or 1.
Yep.
Right? So you're not going to get a single 0 or 1 back from that and operation. Or at least I don't understand.
No, you're only going to get one bit that's set. You're not going to get a 0 or a 1 as the final result. It's the result's going to be whatever the bit is that
yeah, okay,
is.
all right. That's where I got confused.
But that's why you can just test whether or not it's 0, because if it's 0, then the bit wasn't set. And if it's not 0, then the bit was set. So no matter what position this is in. So if I was testing, like in this case, I was testing for read, but if I was testing for write, right? So this would correspond to the number 4, right? So I could actually test the result. I could say like X and 0100, and I could say is equal to 4 or not.
Yeah, exactly.
Okay, so I could do that. Or if I want to not figure out what this is, then I could just say this thing and that thing is not equal to 0.
But
Why but?
no, okay, no, I see what you're saying. Yeah, that makes sense.
Yeah, this is just an easier line
Yep.
to write than that. But,
No, I see what you're saying. Yeah, that makes sense.
Yeah, because now it doesn't really matter what this number is, because like if I don't really care what this number is. I just care whether or not
0.
I really
I'm
just
following you.
Yeah, like I just, is there anything set or not? You know, it's kind of like what I'm doing with the not. Okay.
Gotcha.
So we are gonna like skip this just because this is a little bit sticky with the octal syntax. So I don't really want to go down that path. So we're gonna play around a little bit there later. But I mean, at a high level, does that kind of make sense? So I can use and to kind of peel off. So here's your first real use of and, is like to peel off a flag. So I want to see whether this bit is set in a given number. That's important. Like, so say like now back to the example that I was just telling you with the Nintendo controller. A Nintendo controller has 8 buttons. Right? It has 4 directions on the D-pad. It has select start, right? So we have 2 of those. And then we have 2 buttons here. We have an A and a B. Mm-hmm. Okay, so there's 8 of these total. Funny, 8. That's convenient. Was that an accident? I think not. Okay, so what do we do with these 8 values? Well, it would be really nice if they were presented to us like 8 at a time. But how many wires would that require? Well,
8.
You'd need at least 8 corresponding to each of these. You'd also need another wire for ground, and then you'd need another wire for clocking. So, you're 10 wires in if you go that way. So that's not great. So keep in mind the cost is like directly proportional to how many lines you're using. So what's inside a Nintendo controller if you crack it open? Well, there's a shift register. And the shift register does kind of what you think it's going to do with that shift word. It basically takes all of these values. The shift register is wired one to each of these buttons. I actually ripped one apart on stream just to show people this, but it's really, really simple. It's just the shift register in here, and it sends the thing out. It has a data line, which is where the value is going to show up. It has a clock line, which is how you can tell it when you're ready, and it has a latch. And latch says freeze the state of the controller. Okay, so how many buttons can be pressed on a Nintendo controller? And this is a trick question. At the same time.
My earliest Nintendo was an N64, so I am not sure.
Okay, well, I mean, just looking at it, there's 8 possible buttons, but they can't all be pressed at the same time because have you ever used a D-pad before?
Yeah.
I mean, you can't press like up and down at the same time.
Yeah.
So you can't press left and right at the same time. So you can only, like, not all of these could be lit up at exactly the same time. But what I will get if I try reading this thing in is I'm going to end up with a bunch of values, 8 of them, in fact. And I'm going to get them one at a time, which is why it's called a shift register. Because this is basically the hardware version of what we just did with this shift operator. So it basically kind of like reads one of these digits in, and then it shifts it over, and it reads the next digit in, and then it shifts it over, and then it reads the next digit in. So when we decode this thing on the line, when we're actually reading the data line, we're going to shift these one at a time, and then we're going to build up a byte. So this is actually this is bit banging. It's kind of generically referred to as bit banging. So if we were going to read a Nintendo controller, that's how we do it.
And that is fast to just like shift everything over by one and build up a byte and send that out. That's fast.
It's certainly slower than reading a byte at a time. I mean, what would be faster would be I read the whole thing in one swoop, right?
Yeah. Except
that would require 10 wires, which is directly related to cost. And Nintendo cares about the cost because it's not just the cost of the 10 wires, right? It's the cost of the connector, and then it's the cost of reading it onto the board, and it's the cost of all the protection diodes and all that. I mean, there's a hardware cost associated with every wire. So serial, this is a basic case of parallel to serial conversion. So parallel is like you have all of these things at the same time, right? So like all 8 of these bits could be 1 or 0 depending on what the controller's state is. But serial is I'm going to read them one after the other. So I'm going to read these one at a time. Okay. Hey, what's up, Sunny? How you doing?
Hi, Sunny.
Last miles. What baffles me is the amazing number of programs that walk around who've never seen bits or basic essential bit out. Last miles, I agree, and that's why we're doing something about it today. And that's why we're going to earn our scotch. Okay, so we can read Nintendo controllers. We feel generally good about this at a high level.
I mean, it's the same logic I learned in philosophy. It's just turned into numbers. So
okay, but we're not doing that Aristotelian stuff. We're doing.
I mean, it's if you were honestly, if you looked at like the discrete math proofs that I did in college, it was so many variables and symbols that it looks like math, which is why a lot of people struggle with it. Yeah. But honestly, it's basically the same ideas. I think what I have to remember is that I am used to applying those ideas to larger abstractions, and to apply them bitwise is really what this is. Just the only distinction here is I need to remember apply them at the level of a bit versus applying them
Yes.
at the level of an abstraction.
And that's usually where people get tripped up.
Yep.
That's like it's super obvious at the bit level, and it's not at all obvious when you're looking at like the numbers. So don't look at the numbers. Okay. Great. I'm gonna give us a nice big check mark.
Yay! I get a gold star.
And we're gonna move on. All right. So let's talk about the heap. All right, so topic 2. We got to get through all the rest of it. So, okay, we'll go bit banging a little bit.
Yep. Okay, hold on. Sorry, I got a work message.
Uh-oh.
No, we're good. All right. No, you're fine. I pushed some changes right before dinner, and there's always that panic when you do stuff where you're just like, I'm pretty sure this is good, and then you get the message, so you're like. But no, all is
man,
well.
you just went like YOLO on it, didn't you? You just like throw that code out there and YOLO it out to prod.
After a lot of testing. So I was very confident in it. But nonetheless, you get that like and you're like, ugh. So no, we're all good. Okay. Everything went
okay. I'm sorry that you had that moment, but all right, just we're gonna switch it up here. We're gonna get more bluish. That's kind of not a nice blue, is it? Let's go. How's this green looking? That's a weird green. Ugh. Okay, that's a nice green. I like that. Let's go heap. All right. So, what are we doing with the heap? The heap is green because it's infinite, right? It just keeps on growing. That's not at all what happens with the heap. But, okay, now, do you remember what I told you very briefly about the heap, and then I just like quickly didn't talk about it at all, and then we just...
I remember it's not the stack.
Yeah, it's not the stack. That's great. It is not the stack.
That's about all I remember.
Okay, that's
it sounds like
super
the stack,
important.
But it's not the stack.
It sounds like the stack. It acts like the stack. It walks like the stack. It talks like the stack. It is not the stack, and there's one major difference from the stack. Do you remember what that was?
I have like a feeling, but it's not something that I could entirely put into words. I remember us talking about like.
Okay. Sorry. Go ahead. Tell me your feeling.
No, I remember that even though this is a wrong metaphor, that when you described it, the first thing I thought of was like RAM versus hard drive.
Okay.
And so that the heap reminded me more of RAM, and the stack reminded me more of hard drive. And I don't think you could write things into memory in the heap, but the heap was like temporary storage or something. And so,
okay.
Yeah, I don't really remember,
that's fine.
But that's kind of the
that's on
feeling
me.
that I
have not explained it, so we just really quickly talked about it. So the stack, let's just talk about the stack for a moment. The stack is where we're usually talking about stack frames, and because we're the kind of people we are, we draw the stack as growing in which direction? Do you remember that? Okay. The stacks of coins grow up.
No, we grow down.
Yeah, we grow down.
I remember it being like there was some fancy pants word for it that people were using in chat. And
there's all sorts of fancy pants words. We're gonna try to avoid fancy pants words, but I'm sure chat is gonna use them. So in our world, we're gonna talk about the stack growing down. All right.
The heap is not.
The heap is not the stack.
Yes. And it's also not the chunk.
Is not the stack. Actually, the chunk should be in the heap. We put the chunk
should be in the heap.
Yeah,
because it's a pool.
We actually did chunk it onto the heap when we mallocked the chunk, as opposed to not mallocking it. So, okay, so we talked about the stack growing down, and I quickly told you that the heap grows in the opposite direction of the stack.
Okay.
So the heap typically, now again, these are not hard rules. Different architectures can do
this
differently. What does this
actually mean? I'm so sorry, but like...
Oh, we are totally going to talk about that, but you don't get to...
Because I thought it was like a convention for how to refer to it, but if they're opposites, I feel like there's got to be like a hardware component to this, or is it just like
there are
convention?
It depends on the hardware.
Right, left to right, or right to left.
Yeah, that again depends on the hardware. That's exact. It depends which conventions you adopt. So typical conventions, they're growing into each other, and typically, so in a given piece of process memory, you're going to have the process memory being like a process is a word for program that's running. So we can just call this a running program. So when I'm talking about process memory, then I'm using the stack when I'm doing function calls. Typically, I'm putting parameters onto the stack. So this is like when I call a function, they go onto the stack. When I get out of the function, they come off the stack. And that's the stack is typically growing down from whatever the top memory address is of the process. So if the process is built to run in, say, like 100 is the top of the memory and 0 is the bottom of the memory, we're just going to pretend this is a microkernel. So then the stack is going to start at like memory address 100. So this will be memory address 100. So if I have a pointer to this, it's going to be 100. And if I take the next 4 bytes of memory, say I go and I get myself an integer here, then I'm going to burn myself 4 bytes of memory. These are all single byte chunks. These are 8 bits wide. So then 8888, there goes my 4 bytes. Then my stack is going to be here. And if I allocate another number, then it's going to be 8888, and my stack is going to be here. I'm running out of memory. Mm-hmm. Well, at least on my diagram, because it wasn't really drawn to scale. But let's clean that up a little bit. All right, so that's how the stack is growing. And then when my function returns, it gives that memory back, because that memory is only local to that function.
Right.
Okay. So that's typically what's happening in a stack frame. Now, the heap, I told you, is going the other way. So it's starting down. It doesn't start at the bottom of memory, because typically this is where the program itself is. This is called the text. So this is like, the text would be like the text if a program was a book, then the text would be the instructions to follow to read the book, right? That would be the words in the book. So this is referred to as it was a very classic world back then when we used to refer to like program binary as text. So,
okay.
It was a long time ago. So anyway, so we called that the text, and then there's some other stuff that's usually sitting around here, and I don't want to talk about that too much. There's things like the data segment, and there's initialized data. Sometimes there's this uninitialized data. Sometimes you can have as many segments as you want depending on your linker, but we're not going to get into. This is
where I get a segmentation file?
Oh yeah. Yeah, because all of these are segments, right? It's like, okay, I'm giving you this part, that's the text. Okay, I'm giving you that part.
Is the segmentation file just a fault with your segment?
Yeah, it's when you reach over a segment. So like the most common place where it happens is up here. Like say you go and you access this memory that's up here. That's not your memory. This is like soup Nazi. Okay. Like no soup for you. Okay, that's segmentation fault, right? You cross the boundary there. That's it. You're out, and it kills your program. So actually, again, you're lucky if it crashes. But back in the day, you used to just write into somebody else's memory, which was even worse because their program would crash. Okay, so the stack just kind of kept growing down. The heap did exactly the opposite thing, and it would point up. And there was a notion of like where it was at a given moment. On the stack, we called that the stack pointer. On the heap, we can call it the heap pointer if we want. Has other names, but and that just kind of tells you where that heap is going to come from, and it sort of just grows up. Now, in between these two is actually where we decided to allocate a whole bunch of dynamic libraries.
In between the heap and the stack.
Yeah, we said, nothing's ever going to grow into there, but if they do, we'll just let them. I mean, the idea kind of being like, crash your own program and don't take down the whole system. So the idea being like, make it like, not that this worked perfectly, but the idea was that if you kept taking memory, you would sort of eat your own memory. Like at some point, your stack would overflow.
But you overflow into yourself.
You would overflow into, say, your heap.
So it's like protection.
Yeah, so okay. Like protection maybe for the system, but not really protection for you.
Yeah.
But the idea being that like you wanted your like own program to crash, like okay. From the operating system perspective, like the programmer was like, nah, I want all the memory, it's mine. So as Last Miles is pointing out, it was a real thing. So actually my hatred of Emacs dates back to that era. So that's
you hate Emacs?
Yeah, that's because Emacs for people that know what things like the heap and the stack and bits are, then Emacs actually stands for eventually mallocs all core space. So that's because Emacs was like a beast, and it would just take all of the memory on the system. So anyone who was running Emacs was being very rude to everyone else that was on the machine. So that's kind of where my issues with Emacs stem from. They have nothing to do with the actual modern editor. But okay. So we briefly mentioned that there's this dynamic libraries thing, and then we briefly mentioned that there's this stack. Well, actually, we've talked about the stack in a lot more detail, and now we've mentioned that there's this heap thing. Typically, when you're mallocing stuff, and this is not every implementation, the standard doesn't say anything about it, but back in the day, this was very common. Malloc would take from the heap. So this is why I told you we could take our chunk allocator, and we could just malloc a chunk. It would come from the heap. We didn't actually have to malloc it at all. We could take it directly from the heap ourselves if we wanted to. And that's what we're going to do today using the sbrk command. So this is about adjusting where these break levels are. This is a kernel level function typically. And it says like, I want to adjust where things are going to be. So this is kind of the key insight into that world. This is typically our boundary. Now, we're not going to write a full loader. We're not going to have to deal with like pulling our text off disk in order to be able to run our program. We're not going to deal with initializing our memory. We're not going to deal with initializing the stack. But we could do all those things if we wanted to in C. And in fact, in microcontroller land, typically we do. Yes, last miles, really. But we're not really going to get deep into sbrk. She did write her own version of malloc, by the way, last week. So.
You missed it.
Yeah, that was pretty
Chonk
cool.
alloc. You got to be part of Team Chonk.
We have Team Chonk. So I'm just going to throw that up here. This is for Team Chonk.
It is for Team Chonk. Team Chonk knows where it's at.
Okay, so Chonk really wants to live here in the heap, but Chonk started life off over here in the stack, and that's all right because we're gonna deal with that. So. Great. Now, one last thing, and this is where we're going to start programming today. Have you ever seen /proc?
Sorry, what?
Yeah. So this is really kind of about Unix internals, but there is a directory. So / is always kind of the root on it, sort of like C:.
Yeah.
Windows.
I'm more familiar with Unix than I am Windows.
So. In Linux, actually just about every Unix, there's this thing called proc, which is about processes. And it's about tracking like which processes are running. And if you look in there, you'll always see a whole bunch of numbers. Like, there's like 117 and there's 1 and there's 1248. And then, whatever the process identifier is, which corresponds to a program that's running, is going to be in there. So if you look on a modern computer, you're going to see a lot of stuff in /proc. I don't know if you have a Linux box up and running, but if you just peek into /proc, you'll see a whole ton of things. Now, how do you know what your own process ID is? Well, there's something called getPID, and you can actually ask the system for it. So that's one way to go, but you don't actually need to worry about that because there's this handy little thing, which is called /proc/self. And guess what that refers to?
The process ID of the currently running.
Yeah, this just becomes whatever my PID is.
Yep.
All right. And then in here, there's something called maps. And this is what we're going to start off programming. We're going to go look in this file because this tells you what is mapped where in memory.
So memory addresses?
Oh, yeah. Well, let's go find out. So that's actually our exploration. So I think we're going to come off the whiteboard and we're going to get... Actually, we're not going to be doing me coding. We're going to be doing you coding. So this is, let's go take a look. Now, proc, keep in mind, this is normal Unix file system stuff. So we can just open it like normal files. And this is just a text file. So you can imagine this is sort of like maps.txt in a if this was a Windows world. So, but we're not even going to write that because it's blasphemy on the Unix system. So go ahead. Why don't you open that file up and show it to us on output?
Okay. What directory? Or I guess I can just use an absolute path.
Yeah. It's we're not using open.
I forgot.
I didn't teach you to use open. Never use open.
I don't even know what open is.
Well,
that was just me accidentally
dark,
dropping it out.
That's dark magic. I don't want to get into that. That's the old school. That predates like the STDIO. Every time we open, yeah. Let's be good C programmers. Well, try.
Okay, so
it's just a text file, so I can read lines.
do I need can I use my normal buffer size for this, or?
Yeah, well, let's find out. You're the programmer. Yeah. Time to put all those skills to use. We're in like the last class here. Well, second to last for the basic course. What did I tell you about that? Always use a specifier. Thank you. It is new line terminated, so you're not going to need to add the new line. Assuming that your thousand's big enough, but we'll find out. Okay, that's one line.
Okay.
How many lines are in there?
How do you get the size of a file? Can I just use size of?
No.
I'm guessing not.
Yep.
Stuff never works the way I want it to.
No. We did actually see this operator when we were doing file parsing when you didn't know the size of the file, and that just like now. You don't know the size of the file. So at the end of a file, using standard stuff,
there's like a terminating byte or something, right?
Yep. There's an end of file mark. And you don't need to worry about how that is spelled out in the system because we're just going to use a function that knows how to find it.
Okay.
Which is FEOF.
Okay, vague memory. It's been a few weeks since we used that one.
Oh yeah. Well, we haven't parsed. Yeah, we haven't done much parsing. Now we're not going to parse. We're just going to dump out. We're not. Don't worry. So if I go and so how do I know when I'm at the end of the file? I say as long as I'm not at the end of the file.
Mm-hmm.
So as long as implies what kind of loop?
While.
Yep. So while I'm not at the end of the file.
Oh, while loops.
No. You only get one allocation of the memory. You know that don't do that there. I'll start you off here.
So while
chat, by the way, you're killing me. Let's not talk about the scotch yet. I'm
craving it. What
trying to get through the lesson.
Hold on.
Oh no, it only takes one. I'll tell you right now. It takes one argument. It takes whatever the file is.
Okay, and that'll just get. So what does it return? I'm sorry.
It returns a value which, if it's you can just not it.
Okay, so while not.
Yeah, while I'm not at the end of the file. It reads like English, except it's EOF, end of file.
EOF. Oh yeah, free. All right.
Okay, but you've been in Python too long because our whiles need to have these.
The parentheses, yep.
And this does not have a terminator. Yeah. Okay, and then we have to close that. Yep. So that's our basic loop right there.
Do I? It's indented?
Yeah, it should be.
Indenting makes me happy. Okay.
Now, this will do one extra read for reasons that I'm not that interested in, so don't worry about it. Just go ahead and type it out.
All right. Let's clear the output.
Oh, we got a lot of stuff, didn't we? And we got a lot of big numbers, didn't we? Okay, This is real memory. Harris, by the way, is in shock at your hair, I think.
Who is? Oh, Harry Studios, hi. You missed stream last night.
Yeah, it was there. So I'm going to just show you, I'm going to walk you through real fast. So stuff, so this is web input is the name of your program. I always compile it to be web input at the moment. This basically is telling us kind of where our memory is going to get started. So
it looks like memory addresses, but is that like...
Yeah, these are memory addresses.
It looks like memory address like blank through another one, and then the permissions, and then something else, some number, I don't know, and then a time, and then another number.
Yep. We're not going to worry too much about that format. What we are going to worry about is the first thing on the line and the last thing on the line. So this corresponds to some sort of address, and this corresponds to what's there.
Process ID.
Yep. Now, if we were fancy with our parsing, we could actually just snip it. But I told you don't have to do parsing tonight. So that'll be your homework.
Oh boy.
And so what we do is we're getting a range, and then we're going to see like what it's assigned to. So that's kind of like what's happening at a high level. Now, all of this memory is sort of mapped to whatever our executable is. And then what's this?
I'm sorry, hold on, I'm waiting on stream. I can't see your highlights. Hold on. Heap? It says heap?
It says heap. That's where the heap is. That's actually why we're looking here.
Okay.
Because we want to see how memory is organized. So this is actually the heap. This is where the heap is at the moment. And we're going to find that out using the sbrk command in a second. But that's the actual, that's it. Now, the next thing you'll see, I know the hair is fun. It's all right. It's all right. This is super complicated, but
no, I'm following you.
So what happens after the heap? Well, I told you what you were going to find there. You're going to find a whole bunch of libraries. So these are your dynamic libraries that are in use. So we're using libc is mapped here. So this is actually where your function calls are going for things like strcopy and feof. And libc is here, and libc is here, and libc is over here too, and that's fun. So there's and then there's LD, which is the dynamic loader itself. So that's actually what's responsible for doing all this work for you behind the scenes. And then we see some other junk. So there's some stuff that's not specified. There's some more libraries. Now, depending on your program, there could be a lot of libraries or not. Right, depends how many you have linked in. So if we added CaaAL, which funny that we were looking at that earlier, then we should see it here. Now, what's the next thing we see that I've now highlighted for you, if you can see it?
Give me 1 second, I'm catching up. Stack.
Okay, and we're finding the stack lower down, except if we're looking at these addresses, they're higher up. Right, remember we started like on 5.
I'm not going to be able to start probably. Okay.
Well, I mean, just looking at it here, we'll copy some of that over. But this is basically kind of where the stack is, and this is kind of where, let me pull out the heap. This is where the heap is. So if I just compare these two numbers, I can quickly see that this starts with a 5 and that starts with a 7. So this one's bigger than that one. So in the notion that I'm drawing the stack with the stack is growing down, it's growing down from high level of memory, and the heap is growing up from a low level of memory, and it's getting bigger. So that's actually where they are. So if I want to Stack Overflow this, I need to do a lot of work. There's a lot of numbers between these two.
Wait, hold on. Look at this for a second. No, but hold on. Processing, please.
Holding.
Hold. And then the heap. And the heap. Okay, that makes sense. What is VVAR?
Don't worry about it.
Oh, okay.
There's also VDSO. There's a whole bunch of other stuff that you get.
I was just curious because it was the same notation that it's been using for like stack and heap, and then it had these other terms that we've never discussed.
It's important. It's more important if you want to get into operating systems. It's not so important for C because this is more operating system dependent than it is like DSOs and syscalls. These are actually where some of the lower level operations are happening. This depends what version of Linux you're running. This depends if you're even on Linux at all, or So this stuff I'm not going to get into because it's not really kind of C related. The stack stuff is, if you want to build an operating system, this stuff is more interesting.
We need Chonk OS.
Yeah, if you want to build Chonk OS, then
pledged to make Chonk OS.
then we can start worrying about those things. But anyway, so there it is. There's your stack. There's your heap. That's actually where it's hiding. Now, if I wanted to read these permissions, we now know how to deal with bits. Now, I don't want to torture you with the example I had. So the lightest example I could come up with, which I think is
okay, sorry,
fairly safe, if I may. So anyway, that's our memory organization. So if you're ever wondering, this is actually where you can look. You can look at this proc self maps, and you can actually see what the allocation is. Now, this changes, keep in mind, every time I execute the program, because we don't know where the operating system is going to throw it in RAM. Right? It doesn't always throw it into the same place. A running program stays more or less in the same place, but if every time I run this thing, I'm starting a new program, so it may or may not land in the same location. In fact, it's likely it won't. So that brings us to our last, for this part, that brings us to our last command, which I sent you a man page for before.
Yes.
And that is not f.s, that is sbrk. Sbrk. Okay, so what does sbrk do? Well, it changes the break where that heap boundary is. So that basically, if I tell it takes one argument, which is a number, and that's like how much more memory you want the heap to grow.
Which does that? So there's like this no man's land that's between the stack and the heap, where you set a lot of these.
It should stay a no man's land, because if it ever becomes a man's land, then our program's going to crash.
But so lucky. Does changing the breakpoint for the heap, does that change the size of the stack?
No.
Okay, good. All right, so that it's the no man's land that's shrinking.
It's on the heap side of the no man's land. So if it ever changed the stack, that meant you grew.
I need a map. Okay, no.
We draw it, right?
I know. I'm trying to visualize it.
Okay, actually, here I will give you that. So let's just quickly go back to the whiteboard. So this is when I was looking at this thing. I had. Sorry, I'm just throwing the glove on here. I had the stack was growing down. And the heap was growing up. Now, there was some other stuff down here which we're not going to worry about, but because we just learned about it. And then we knew that somewhere kind of in here is those dynamic libraries. And we just saw that they're all there and they're happy. So this is actually kind of where you're calling. libc in particular was here. So when you were calling like feof and you were calling fopen and all that stuff, that was actually being resolved to this area. So that's where that functionality is living at the time that you're calling it. But this, however much of the heap is, quote, live, this is...
So in use.
Which, yes, in use, is kind of where the break point is for the heap. So if this is kind of where the end of the heap is, this is some location in memory. Now, if I grow this because I want to have more memory, like say for the chunk allocator, like say I want to have like 2 megs, then this is going to have to grow. And in order to grow it, we're going to have to ask the system, hey, it'd be really swell if you gave me 2 megs, which would be 2 times 1024 times 1024, because this is bytes and this is kilobytes. Well, this is bytes to kilobytes and this is kilobytes to megabytes, and this is, I want 2 of them. So So this amount is how much I want you to go up.
Okay.
I want you to grow that break point. This was traditionally referred to as the break. So that's what sbrk does. And when it returns, it tells you where it returns a void pointer, which corresponds to where the heap now ends. So you can sort of tell, like, did the allocation work or not? Because if the heap didn't change by the right amount, then you know you didn't get that memory. That was a little fast at the end. So just looking at the heap side of this drawing. So I start my heap here. I grow it by, say, I don't know, 16 bytes. So this address in memory should be whatever this used to be plus 16.
Right.
And then now that's where heap is.
But so memory addresses. I guess when we were talking about pointers, right? And we use this metaphor of addresses to houses.
Yep.
And we talked about things like
metaphor.
But we also talked about things like memory padding, which made actually a lot of sense.
Don't worry about padding. We're not getting into padding.
So no, but my question is, why bother having all of those memory addresses if, for the most part, especially on modern day systems, so this might be like a modern day question, but like, you, for the most part, won't be concerned about an overflow of 8 bytes, 16 bytes, if most of your memory is written in chunks that are larger, right? And so when you draw these levels, these are larger than like 16 bytes, right? So why would it not say, let's say we're dealing with a very, I don't know, small system, and so each of our little chunks that you are drawing horizontal lines for is 8 bytes. Would it not be that it is 2 memory addresses above that, not 16?
Yes.
Okay.
I wasn't drawing to scale. But you're absolutely right. If these are 8 big because of our memory organization, then yes. Now I can tell you that on our modern system, these are usually
much bigger.
Yeah, they're usually 64.
64, yeah. Okay.
So,
no, that's fine. It was just.
But yes, you're right. I'm not drawing to scale anymore because now we're starting to talk about big numbers.
Totally fine. Totally fine. It's more for my own like verification that I'm understanding things.
I should have warned about that. Sorry that I dropped scale. But so
totally fine.
Okay. Now if I need 16 more bytes, then I'm just going to say, all right, system, I want you to grow again by another 16. So now the heap is going to be here.
Right.
You're not
but
here
at some
anymore.
Point,
you're here.
Right. Can you draw the stack though?
Sure. I don't want to draw it to scale.
No, that's fine. That's fine. Let's just pretend it's a very, very tiny stack or something. Or we're in some MC Escher stack land where stuff is just...
I'll use the dots in between to indicate that there's
go.
a lot of space here. So the stack pointer is going to be pointing to wherever the bottom of the stack is.
Right.
Okay. So that's important when we get to Nintendo's. So, because there's not much stack space, by the way, it's really easy to blow out your stack. Okay.
Oh, yay.
You really do have about 200 bytes. That's it. So.
It's serious?
Yep. And if you write into that whole 200 bytes, you're probably writing into the 0 page, so you're probably calling functions and not even realizing it. But we're not going to worry about that today.
Can I add a topic to the
Sure.
Scotch?
Yes.
So I don't know. I read this article that was obviously a popular, like, pop science article, so it wasn't really going into the details about how on the first moon landing, the code was somehow like sewn into
yeah.
Like, okay, and I just like I literally just my brain was like, no.
Okay.
Like what? So I would like you, expert of all things code related, to explain to me what the heck is going on with that. Because it sounded really freaking cool. And then, sorry, this reminded me when you were talking about these very small machines, and it reminded me of how limited the early spacecraft were in terms of memory.
Yep.
And you know, one thing led to another, and I've been meaning to ask you about
every bit there mattered.
Yeah, right?
I could tell you.
One, that's really cool, but also two, I'm sorry, sewing. Wait, what?
Yeah.
So.
Well, we don't talk a lot about physical processes. Well, all right. Let's save that for
Yeah, sorry. That was I figured that would be a good Scotch.
I'm itching for the bourbon before we get there.
Code and in space, so it's like a good. All right,
but yes, it is super cool. And actually, I was just reading about their multiplier. Anyway. Totally.
Yeah, save it.
Totally
I will be on topic.
All right, so if we want to move the heap, then we do it by. So if we want to move the stack, this is typically a register. So there's actually a register that's usually referred to as the stack pointer. So I can actually just do math on that register directly. The heap usually does not have a register. It may or may not have a register. It depends on what kind of system you're on. So this is typically an OS call, which is why we're going to be using sbrk. And sbrk basically returns where you are right now, and you pass it how much. So this is basically like how far do you want to move the breakpoint of this being the breakpoint.
Okay. So what it is encroaching upon, though, is that neutral no man's land.
Neutral zone.
The neutral zone, right?
That's absolutely. A lot of these people were Trekkies, by the way. So, okay. So this we specify how much, and it returns where. So using this, we can smoke out where the heap currently is because we can just say sbrk 0. So if we say move the heap by 0 bytes, then it'll tell us where we are. So let's start there.
Okay.
Okay. So ready, code. Now, I'm just going to you're going to need this for a little bit, so I'm just going to leave it here, but let's just comment it out to keep it out of the output. So I just told you that sbrk works by specifying how much, and it returns a void pointer, which is where.
Yes.
Yeah, rope core memory. Nice, love fun.
Okay. All right.
And not to press, but the faster you do this, the faster we get bourbon.
Oh no, I'm sorry. I was writing notes. Okay. All right. So.
Oh, and thanks for the follow, Sentinel. I missed that earlier.
Okay. So our goal here is to increase our heap memory because...
Well, let's find out. Let's start off by where is the heap. So we could parse that maps thing.
Yeah.
But I just told you another way we can get it from sbrk. So let's use sbrk.
Okay.
And I'm just going to help you a little bit because I'm thirsty.
Yeah.
Which is, you're going to need this in order to be able to call sbrk.
That's good. That's good to know. Okay. But so the sbrk, we need to know how much.
Well, tell it nothing. Yeah. Don't move at all.
Oh, right, because that's how much to move it, not how much to allocate. Okay, yep, we're good.
Well,
so
moving it is allocating. That's.
So first, this is just placeholder. Don't look at this. Returns where, so a memory address. So this is going to be a number technically, right? So
it's
I'm going to need
pointer to address the memory, which is a void pointer, because it makes no implication about the semantics.
So
that's the where.
Heap?
Okay. Heap thing. What's that rogue space doing there?
What rogue space? Oh, yeah, sorry, that was me thing.
Excuse me. The heap begins. In a world where the heap begins.
Sad face. Is it because it needs?
We gotta pass
it's not
it. How much we want
break.
sbrk to move it by.
So I can't just leave it empty.
No,
So is there...
Tell it 0. That's okay. And this D...
Is it because it's int and it's...
Yeah. So it's telling
fine.
you, by the way, at the bottom, it's saying, no, you know what? It's memory address. You really want to use this %p. So go ahead and use %p. It's very nice these days, very polite, and it tells you. Oh, look at that. Nice hex.
Yay!
And we can see that that happens at roughly the same sort of magnitude as the earlier run. You'll notice it's not exactly the same as the earlier run.
No.
Okay, but if I run the program again... Oh, look, it's different.
Yeah.
It's the same general area, but yeah, it's a bit different. Oh, look at that. It's somewhere else. It's somewhere else. It's somewhere else. All right, we don't know where the OS is going to put our program. In fact, our program should not know where it's going to end up in memory.
Okay.
We sort of want our program to work anywhere that it happens to land in memory, which is why we use standards like C, and we try to do the good C, but we can do the bad C if we want. And this tells us where we are, but it's relative to that execution. So you can't compare these heap pointers across executions.
Okay, that makes sense.
Like that's the heap pointer for the program that just ran, and then that program terminates. So when you run it again, it's going to be somewhere else.
Yeah.
So, all right. Now, let's go ask for 16 bytes of memory. Well, let's remember where we started too.
So you want, can we, let's see. Can I override it, or do you want another?
No, I want another variable. Okay. Nice. Okay.
What? It's the same.
Linux lies to us all the time. I mean, we can ask for a lot, right? We can say like, all right, you know, I want that 2 megs that I told you about.
So,
and it's
does it
still
not give
the
it
same. Now, I told you before that Linux uses optimistic memory allocation.
Right.
So, despite...
Does it not give it to us unless we use it?
Yeah, that's called touching the page. So we actually have to start using the memory to get it to...
Gotcha. So we need to put something, or we need to have our program use that much memory. Right?
Yeah.
Sorry, I'm writing, copying and pasting, writing notes and stuff.
Last Miles is asking for another 1024, so we'll just sneak a little bit more. Yeah, we're still running into the same sort of issue here. So
why are we doing what, Harry Studios?
Don't look at what
the heap.
Don't read what Last Miles said. Don't read what he said, because that's he's totally giving you the answer.
Oh, I was reading Harry Studios.
Right.
I wasn't reading Last Miles. Okay, so what are we doing?
How are we going to use that memory?
Let's think about this. Accidentally saw what Last Miles said, so he's
all right. Well, then Last Miles is right. That's what we want to do.
I don't remember what Mem Set did. I'm sorry, though.
That's
so
all right.
I mean, I wouldn't have the answer anyway.
My
guess would have been think of something that would take up that much room and like.
Well, if you didn't,
set it.
if you didn't have Mem Set, then you could just loop through and set it to 0, right?
Yeah.
Okay. So No, you're all right, last miles. Don't worry about it. Yeah, this isn't a test if last miles knows how to touch the memory. Okay. So this is, by the way, something that Java does all the time. You can ask it to do. It's called pre-touching. So you can basically say, I want to guarantee that I have that memory. Like, so I want, before you kind of do anything with it, like force the OS to sort of like definitely give us that memory. Because right now it like may or may not give us that memory. So Mem Set is basically a way to set one value for an entire range of memory. So it's sort of like str copy, well, except it's not copying. It's closer to like, B0, but we're not using those crazy Berkeley kids programming style. So basically it just, I'll give you the function parameters for it. So Mem Set this is all you're really going to need, which is this thing. So this basically takes where you want to start, it takes what you want to put in each location, and it takes how much. Actually, let me just double check. N bytes of memory pointed by S with constant bytes C. Okay, so yeah, C is the constant. So it's going to put this value in every location.
I'm so sorry. Go ahead.
It's going to put this value in every one of, I think it was N size T. Yeah. So this is how many. This is what to put there. So just put it 0. And this is where.
Okay. So and then the size, I'm guessing in bytes.
Mm-hmm. Now, we shouldn't have those magic numbers. I blame the teacher here for that. But
oh my lord. Sorry, my mic is...
Wait, I think that's okay. That's a little too much there. So that's...
Oh, plus, yeah, I'm sorry. I was trying to copy and... All right, so...
All right, so if we set it and then we look at it again, because now we need to know where it is after that.
It should change.
Wait. Where did you check the sbrk? Before or after the Mem Set?
After, but we need to...
Yep. So we need to do it again with sbrk 0 to see where we ended up.
I see. So let's just call this... We know that this is already
Save heap start. You're going to need heap start. Because you're going to need it in a moment. Yes, Harris. So in a previous session, she actually created her own version of malloc. I feel like there's no better way to understand an allocator than to write one. Okay. Yeah, let's take a look.
Ha!
Ha!
Change.
Now, here's why. How much memory did you get?
Two times.
No. Not what did you ask for. How much did you get from the system? You're not guaranteed to get all that memory.
6 to 122,000.
Wait, no. It's first of all, it's going to be millions because it's megabytes. But second of all,
I'm just subtracting the two addresses. So
they're in hex.
But
why don't we? You have a computer. Let it do the math. That's why we saved our start address.
Okay. Can I just subtract them?
Oh, Harris, definitely not. We're C programming now, so.
I probably have to make this. This is going to be some kind of integer. Can I just subtract them?
Yeah.
Okay.
It sounds great.
You can subtract memory
Wait,
addresses.
You don't need to. Just you can. Okay, I'm gonna help you with this one. Because
do I have to cast them as integers?
Yeah, that's basically right. That's basically right. But what I want to do, I'm gonna just get rid of this variable. Because
do you want me to just do it right there?
I just want to put it out.
Oh, okay, that's fine.
Let's just get that number. Sure, it'll fit. You'll never have more than 2 gigs of memory, right? So many programs broke. All right. 2.2 million.
Thank you, sbrk.
Now, it totally lied to us because until we did our Mem Set, it was not giving us that memory before. It was giving us exactly the same addresses. So now I don't want to go screwing around with it, but there's voodoo under the hood is all you need to know. Like you don't know what the OS is actually going to do until you use the memory. So pre-touching is a pretty good pattern if you want to be guaranteed that memory. So for example, if you're running your chonk allocator and you want to make sure that chonk got the memory that chonk was promised, and that you're not dealing with a bug that's related to the system and you want to be able to report things, then you'd better do the sbrk and you'd better touch the memory to make sure that you actually got it.
Gotcha.
Okay. Does that all make sense?
Yes.
Great. Now do a binary operation all... No, I'm just kidding. That's